Today I'm going to take you on a journey into the world of fractals, specifically the Koch Snowflake, one of the earliest fractals ever described. We'll explore the beauty of recursive geometry and see how coding with TurtleStitch can bring these mathematical patterns to life through embroidery. In 1904, Swedish mathematician Helge von Koch discovered this snowflake fractal design. It was one of the first fractal patterns to be described. A fractal is a geometric shape in which each part resembles the whole, a property known as self-similarity. This snowflake fractal is also considered a recursive design because its pattern repeats itself at smaller scales. The Koch Snowflake shown in this slide is a level 3 Koch Snowflake. Constructing a Koch Snowflake. 1. Take a straight line and divide it into 3 equal parts. 2. Replace the center with 2 sides of an equilateral triangle. Notice that the straight line is replaced with 4 smaller segments using turns of 60 degrees left, 120 degrees right, and 60 degrees left. This 4-segment shape is the basic unit of self-similarity that repeats throughout the Koch design. 3. Repeat the division. Each segment is replaced with 4 copies of the previous pattern, each 1/3 the size. Instead of drawing straight lines, the previous shape is repeated at a smaller scale. 4. In example number 3, only one side of the snowflake is generated. To complete the full Koch snowflake, as shown here, the process is repeated 3 times, turning 120 degrees between each side to form the complete shape. 5. Another level can be created by further subdividing the sides. Notice that while the overall size of the snowflake remains the same, the design becomes increasingly detailed and dense. In this slide, 2 Koch snowflakes are shown, a level 1 on the left and a level 2 on the right. What do you think the next snowflake will look like? The next slide will show you the iterations leading to level 4. Coding a Koch snowflake. The diagram above shows 5 iterations of the fractal design, created using a recursive block called Koch curve. The first figure represents level 0 in the recursive program, or stage 1 according to Koch's paper. Each subsequent figure represents the next level or stage, continuing the pattern until level 4 is shown in the diagram above. This process can be repeated indefinitely. While the overall size of the snowflake remains constant, its details become progressively more intricate and infinitesimally small. Check out my TurtleStitch program to see the transformations in action. The link to this TurtleStitch program can be found in the YouTube description. On the left, you will see the recursive block that I used to create the embroidered Koch snowflakes. Now let's deep dive into this code. TurtleStitch uses coding blocks to control the turtle's movement. The block is named Koch curve. This block is a great example of how recursion works in computer science. The program calls itself over and over at smaller and smaller scales. The Koch curve block draws one side of the Koch snowflake. It takes 2 inputs, the length of the line to draw, the side length, and the level, which determines how many times the line will be subdivided, that is, the recursion depth. Here's how it works. If level equals 0, that's the base case. The turtle simply moves forward. If the level is greater than 0, the turtle calls the Koch curve with 1/3 the length and level -1. It turns left 60 degrees. It calls the Koch curve again. It turns right 120 degrees. It calls the Koch curve again. It turns left 60 degrees and finishes with one last Koch curve call. Each time this happens, the straight line is replaced by the 4-segment self-similar shape of the Koch snowflake, scaled down to 1/3 the size of the previous segment. As the recursion level increases, the pattern becomes more detailed and more fractal-like. Let's examine the code even further to show what happens at each level. When the Koch curve block is executed with a side length of 100 and a recursion level of 0, the result is a straight line since no recursive subdivision occurs. This happens because the base case of the recursive block is reached. When the level is 0, the turtle moves forward by the given length to create a single straight segment. Since only one side of the segment is generated, a 120-degree turn is required. This process is then repeated 3 times to construct the complete Koch snowflake, as shown in the code on the right. At level 0, the code produces an equilateral triangle with 3 straight sides. The recursion and all the fractal details starts at the next level. This level 0 snowflake is the base shape before any fractal segments are added. When the Koch curve block is executed with a side length of 100 and a recursion level of 1, the result is 4 line segments, each 1/3 the length of the original segment from level 0. The shape on the left of this slide shows this clearly. This 4-segment shape is the basic unit of self-similarity that repeats itself throughout the Koch design. To make a complete Koch snowflake, a 120-degree turn is required. This process is then repeated 3 times as shown in the code on the right. The result of the code is a 6-point star because the added spikes create 3 new outward points on the original triangle. At recursion level 2, each of the 4 line segments from level 1 is replaced with a smaller 4-segment pattern, the same self-similar shape scaled down. This increases the total number of segments on one side of the fractal to 16. To make a complete Koch snowflake, a 120-degree turn is required, and this process is then repeated 3 times as shown in the code on the right. The result of the code is the snowflake below. This snowflake has 48 segments. This added detail gives the snowflake its distinctive fractal appearance, a curve with an infinite parameter but a finite area. Can you imagine what the next levels look like? It is shown in the next slide in the embroidered snowflake. Embroidering a nested Koch snowflake. I designed this ornament to showcase 4 different levels of a Koch snowflake. It was embroidered on felt using a running stitch. The design starts with level 1 at the center, progressively increasing in complexity up to level 4. Each level's size is scaled according to a decaying factor, with side lengths following the sequence 300, 172.1, 86.43, and 38. This gradual reduction creates a distinctive visual effect as the iterations decrease in size. The decay factor isn't uniform, which is deliberate. It was done to enhance the visual effect of the embroidery. A satin stitch circle frames the snowflake with a loop for hanging. Check out my TurtleStitch program to see this nested Koch Snowflake in action. The link to this TurtleStitch program can be found in the YouTube description. Koch Snowflakes are a perfect example of how math and coding can come together to create intricate recursive art. Using TurtleStitch, we've coded and visualized both mathematical elegance and creative expression. TurtleStitch is a powerful tool that encourages you to think like a mathematician, problem solve like a programmer, and create like an artist. Even without an embroidery machine, you can explore mathematical patterns, experiment with coding, and watch your designs come to life on screen. When a machine is available, those designs can be stitched onto fabric to connect math, coding, and creativity together in a fun and meaningful way. I hope you enjoyed exploring the mathematical beauty of Koch Snowflakes and recursive coding in TurtleStitch. Please visit my blogs, papercraftetc.blogspot.com and turtlestitch.blogspot.com. There you will find more projects featuring math-based designs. Thank you for watching.